Okay, welcome. This is the FRQ. It has to do with the satellite being moved to a higher orbit and the process of how to go about that. So here's the question that we're looking at. So it says satellite of mass m is in stable circular orbit around Earth at a distance r1 from the center of the Earth. The mass of Earth is me. Derive an expression in terms of these things. Okay, let me jot that down. So I can have the mass of the satellite, the radius from the center of the Earth, I call it R1, and the mass of the Earth, I call it M sub E, but nothing else, well, exotic constants. So, okay, let's see what we can do for this. So you want to orbital speed. Okay, pretty common question to try to get to orbital speed. So the thing that they're looking for you to recognize. So I have something that's going around in a circle, right? And there's a force that's holding that object in place, that's causing that to change direction and go in orbit, and that is the force of gravity between two things, and that's going to equal my centripetal force. That's providing my centripetal force, right? So this is the key thing to recognize. The centripetal force is coming from gravity, and centripetal force I can write as mass times centripetal acceleration, and force of gravity. So I'm at a distance, I'm not above the surface of the Earth, so I have to use Newton's universal law of gravitation. I'll call this the mass of my object times the mass of the Earth over the radius of the Earth squared, right? So these two are going to be equal. So notice that the mass of my satellite is going to go away. Acceleration, well, I can't have that. I'm trying to get to velocity, but fortunately, centripetal acceleration is going to be the square of velocity over the radius. I call this R1. This is equal to G, mass of the Earth over R1 squared. So I'll simplify this and then take the square root. So my velocity is going to be equal to the square root of G, mass of the Earth over R1 not squared. Okay, part one. So now we have an equation for velocity. I'm going to guess they're going to want us to use this, right? So even if I get the wrong equation for velocity, I'll need to follow through and use it for something. Part two says the total energy of the satellite in this orbit, assuming gravitational potential is 0 and infinite distance. Part two. Oh, it says derive an expression for the following. So they want me to derive an expression for the total energy of the satellite in this orbit, assuming gravitational potential energy to be 0 and infinite distance from the Earth. Oh, this is a hint, right? So, what I'm going to do, I'm going to worry about gravitational potential energy. Right. So, part two. So they're saying gravitational potential energy at infinity is equal to 0. Right? So the key thing for this is that my gravitational potential energy, as I get closer than infinity, is going to be less. Right? What's less than 0? Well, negative numbers. So this is going to be negative G M E over radius 1 not squared. Right? So this is my gravitational potential energy at any point. So they want me to find an equation for, what was it, the total energy? What am I looking for? Total energy. Yep. So they want me to find the total energy. Well, I'm going to say my total energy is going to be positional, but I also have kinetic energy, right? So this has some velocity. So I'm going to say my energy is going to equal my potential plus my kinetic. And all of my potential, I'm assuming, is this. So notice I have a negative sign. I'm going to be careful about this. So this is going to be equal to negative G M E over R1 plus 1/2 mv squared. So what's v? This, right? So I'm going to use the velocity from my previous equation. So I have to get this in terms of mass R1, mass of the Earth. Velocity is not included in that, so I can't stop here. Right, so I'm going to keep going for a little bit, and I'm going to hope this simplifies a little bit and doesn't get too ugly. Sometimes it does. So I have my potential energy plus 1/2 mass times now v squared. Well, I square this, and I just get rid of the square root. Right? So this is going to be G M-E over R1. Oh, look. So these two are the same. So I have 1/2 of this and negative 1 of this, so I'm going to have negative 1/2 G M E over R1 not squared. All right, convince yourself that makes sense. Right, so I end up with a negative value for total energy. Yeah, technically I can't have a negative value of energy, but because they insisted that I set the 0 point at infinity for potential energy, I have less than I have at infinity. So that's that. So I know with a negative value for this. This is important and okay. Okay, so far so good. So I have an equation for energy. So then now they say the satellite's booster rockets fire and lift the satellite to a higher circular orbit. This is a radius of 2r1. Oh, nice. So the satellite follows the path from the diagram, moving total distance s, so s is a constant, during the orbital change. The component of the rocket's force parallel to the path, right? So this is important. So parallel to the path. So this is in the same distance, so I can use work, and that force is in the same direction as displacement, so I don't have to worry about components. The force is given by this equation. X is the variable distance. So x is my variable in here. S is a constant. So yeah, what do I want to do? So, well, B, derive an expression for the total work done on the satellite in terms of F naught and S. Okay, so let me switch back to this. So next part, so I know work is going to be the integral of F dx. Right? So it is my force times distance, and this is my calculus version of that. So force times distance. They give me an equation for force, right? They said force has this equation is F naught times 1 minus x over s. That's the force. So I'm going to take this equation, plug it in here, and then I want to evaluate that integral as I go from 0 to s. Right, so s is the ending point. Right, so let me write this out. I'm going to do our work from 0 to s is a definite integral, so I'm going to add up all of those little forces times those little distances all the way along my path, starting at 0 and going to the final length that I've traversed. And this is going to be equal to F naught times 1 minus x over s times dx. Yeah, so now this is a calculus problem, right? So I'm going to pull this F naught out because it's a constant. I'm going to distribute the dx, and then I can separate these into two different integrals to figure out, right? So W is going to be F naught, so my constant comes out of the integral from s. I'm going to have 1 minus x over s times dx. So this is like taking the integral of dx and also taking the negative integral of x dx over s. So when I do that, I'll end up with the integral of dx is just going to be x, right? So this is like having x to the power of 0, so I'll add 1 to the exponent and divide by that, so I'll end up with x. And this one, so I'm going to have x dx, 1 over s. Well, I'm really thinking this is 1 over s times, but now x dx. So I'm going to take this exponent, which is 1, I'm going to add 1 to it, so I'll have x squared, and I'm going to divide by that new exponent, x squared over 2. And I want to evaluate this from 0 to s. Anyway, check the calculus, make sure that makes sense to you. So I can think of it as evaluating two separate integrals, one of dx and one of negative x dx over s. When I plug in s, right, I'm just going to get s squared. When I plug in 0, I'm going to get 0 and 0, so I'm going to get nothing. So this is going to be F naught times s minus 1 over s times s squared over 2. So notice I'm going to get, this is going to cancel once, so this is going to be the same as F naught times s minus 1/2 s. Yep, so if I have 1 minus 1/2, so I'm going to end up with 1/2 F naught times s. And it kind of makes sense, right? So I'm going to have half the initial force over the distance. It kind of makes sense. So it should take less force as I get further away. Okay, so this is my equation for work. Okay, so far so good. What else do they want us to do? The total distance S is equal to 3R. Ooh, nice. 3R1, derive an expression for F naught. Well, in terms of these things, right? So here's how I'm going to think about this. I want to get to F naught. They kind of tried to help give me hints, right? So they had me think about energy. So this is what my total energy is. And they had me think about work, which is this, right? So, so work is going to be, so what I'm thinking the work is going to be equal to the change in energy that I experience, right? So I have a value for work and I have an equation for energy. I just need to look at the energy at those two different scenarios, right? So the energy at R1, right? So this is my general equation for energy that we already figured out. Is energy is negative 1/2 G M E over R1. So energy at R1 is going to be this, right? Negative 1/2 G M E over R1. Energy at my second point, so R2, right? They tell me I'm at twice the distance. Autofocus on that. They tell me I'm at twice the distance. Oh, come on, focus. That's not good. Focus. No, seriously. Focus. Okay. So now R2 is going to be GMME over 2R1. Right, so now telling me I'm twice as far away. So this my change in energy is going to be my final minus my initial. Which my final is going to be this. I'm going to subtract my initial from that. Right? So it's going to be a less negative number, so I'll end up with a positive change in energy, right? Hopefully it makes sense, right? So my final, so negative 1/2 G M E over 2R1. I'm going to subtract this from it, so a plus 1/2 G M E over R1 by itself. I can factor out G M E. I can factor out 1/2 G M E over R1, right? So this is going to be 1/2 G M E over R1, right? So then what am I left with? I'm left with this negative 1/2 plus 1. So I'm going to have half subtracted from 1, so I'll end up with a half. So this will convert into a positive 1/2, and multiply this across, I'll end up with 1/4 G M E over R1. Okay, so seems reasonable. So I double the distance, end up with half the potential energy. Sure. Now I've got a value for energy. I want to set this equal to work. I just figured out what work was. What did I say? Work is equal to 1/2 F naught times S. So the work that I put in there is equal to the change in change in energy. So I did positive work. I should have a positive change in energy. So I want to get to my F naught. So F naught is going to equal. So I multiply both sides by 2. I get 1/2. I multiply. S. What is S? Is they tell me S is what, 3R? Yeah. What did they say that was? S is equal to 3R1. Okay, let's. So this is going to be. Let me just write this out a little bit more clearly. So I'm going to have 1/2 F naught times 3R1 is equal to 1/4 GM ME over R1. So I'm divide both sides by R1, which means now this will become squared. I'm going to divide both sides by 3, so I'm going to have 1/3. Get rid of that. I'm going to multiply both sides by 2. So my F naught is going to equal 2 times 1/4 times 1/3 times GMME over R1 squared. So hopefully this starts to look a little bit familiar, right? So I notice I have my square of my radius, so that's good. So I have force. So this is very similar to universal law of gravitation, so it kind of makes sense that I should end up with the right units at least. And then I'll make sense out of this. Is going to be 1/2 times 1/3 is going to be 1/6. So 1/6 GM ME over R1 squared. So that's my value of the initial force to make this all work out. Anyway, it's a nice problem with a lot of steps, but you kind of have to help them figure out the logic to it. So they had you figure out energy first, and then they had you figure out work. So that's a hint. Take advantage of that. Hope that helps, and we'll talk to you soon. Bye.